She will not
Well, it's certainly a great privilege, and it's always a pleasure to be back in Oxford when I don't have to deal with all the politics. And Philip's introduction was very kind, and being in this new building has got some mixed feelings. The Centre for Mathematical Biology was in the lovely old 18th century house one side of St. Giles. Anyway, what I thought I would talk about are really three things that, among a few that I've been involved in, but I assume that sitting here you were able to read this. I mean, which is really it's a nice description of three-headed monsters, and he got an MA from Oxford. I mean, it's, I don't know what the university was like then, but he's actually a well-known person. The monsters I'm going to talk about are just a little different. So what I wanted to do, if this is going to work, yeah, sorry. Not that I'm a great fan of Benjamin Rush. I mean, he was one of the rebels that signed the Declaration of Independence, but he was a doctor who is best known for his work on the yellow fever in Philadelphia in the 18th century. But what I do like is what he said about anything associated with medicine, that knowledge is of little use when confined to mere speculation. He ended up getting yellow fever himself, and he treated himself in a rather radical way, and he was accused of killing thousands in this way, but I'm not quite sure. It was a very prejudiced time. So let me start off then about really embryos and the whole business about deformations. It's been a subject that's fascinated people for really millennia. And what I wanted to describe was really a theory that could actually be tested experimentally, which is why do you need that one? Both of them, does that help? Okay, fine. George Oster came and spent 6 months, he's from Berkeley, came and spent 6 months in the Center for Math Biology, and we tried to think about how things develop other than genes. Because I'm afraid I have this view that when genes is a closed subject, we still won't know how to build a chicken, because they don't do the work, they just control it. And so we wanted to talk about the work. So if you look at what embryos are at roughly the same stage in development, there's a certain similarity. And these actually are pictures taken from somebody called Hooke in the 19th century, who was very well known and produced all sorts of really dramatic pictures. And he was a well-known biologist. The only problem was if it didn't quite fit in with what he believed, he just manipulated it a little bit. So I'm not sure how human that one really is. But if you look at them, in a sense, it suggests that there really is some fundamental similarity about the production of them. So, I mean, that in the case of a salamander, it's got 5 fingers. You know, we've got 5 fingers. Poor Anne Boleyn, she had 6 fingers. And you remember one of the wives of Henry VIII? The only problem is they cut off the wrong appendage. So what I wanted to describe then was to see how, if we go back to the basics, then there are really kind of 2 types of cells. These mesenchymal cells and epithelial cells. And down the right-hand side, they kind of, they're around the skin. So I'm not going to talk about then. It's the ones on the left. And these are small cells that what they do is they have things called philopodia that can pull. I mean, and they can move around on a tissue. And so when they move around on the, when they move around on the tissue, they deform the environment. So they're having an effect on each other, even though, in a sense, they're not touching. And so what really got us involved in this was a picture that Albert Harris and University of North Carolina sent us, that these are actually fibroblast mesenchymal cells that have some sort of, that do have attraction, and you can see these are the things that pull things around. You can see it there, and you can see it there, and these are tension lines. And so in a sense, it's like these cells move around on these matrices that have got tension lines. It's a bit like a jungle gym. You kind of climb up, you distort the rope, etc., and you can make it either more easier or more difficult, or things like that. So these are the real cells that I wanted to talk. And as I said, it's a friend. Sorry, I keep pressing the wrong button. So it was George Oster that I mentioned. So let's start with the scenario. And what one then has is the cells deform the extracellular matrix. So that's the tissue that they crawl in. But then when they do deform the matrix, that can affect the cell division. And so you start to get a kind of pictorial scenario where you can start to see how they influence each other in such a way that the cells might start to form aggregations. And so all of these things together then end up that the cell motion, there's convection, there's random motion. Haptotaxis is a kind of mechanical thing where in the simplest way, one cell grabs another and moves it along and makes them join some aggregation. So we've got contact guidance. Chemotaxis is where the cells react to a chemical gradient. And so chemotaxis usually means that if the concentration of the chemical, the smell, goes up that way, then the cells move up that way. And so it's kind of the opposite way to diffusion. And say the combination of all this is you start to get cell aggregation patterns. And with a lot of the applications, Philip Maney was a major collaboration in all this work. So what we decided to call it was the mechanical theory of morphogenesis. And so really, we want something as simple as possible, but not simple enough that you can't kind of get some answers to biological problems. So we're going to just have cells, we're going to have a matrix density, and we're going to have tissue displacement. And then we want to see if we can actually construct a practical mathematical model and then examine it and see what happens. I'm not going to do much mathematics. It'll just be maybe a couple of slides as a kind of, a token to the mathematicians. But basically, what you have for the mathematicians, you end up with three equations because you've got three unknowns: the cells, the extracellular matrix, and the tissue displacement. Of course, everybody who's worked in this sort of area knows about reaction diffusion theory. The thing about reaction diffusion theory is that they are nice equations to work on if you're a mathematician and that's what you want to do. If you want to actually find the chemical or the morphogen that's associated with reaction diffusion equations. It was first proposed in 1952, and one was found last year. That really is deferred gratification. And so the next slide, those of you who are not mathematicians, just read the English. The thing is, what an equation does is just try and quantify how things interact. So what you've got is you've got cells that are changing, they're being convected, they're being influenced by contact guidance, the kind of jungle gym sort of thing, and then there's cell division. And so really you just quantify that. That's all mathematics does with a few parameters. Then you've got the tissue, because you want to know how the tissue changes, because that's going to affect how the tissue changes into cartilage and things like that. And so then that's last equation is just how the forces are all balanced together. Okay, and so you've got all these stresses, external forces, and there's parameters associated with displacement. Don't need to, in fact, if one needs an equation to explain what's going on, I always feel you don't understand the problem. And so I tend to like just talk about what they're saying. Okay, so what we did was we took these equations and we did some mathematical analysis on them. And what we found was that if you take just a narrow domain and you put in a bunch of cells and they've got tissue in it, then the cells start doing their thing, they're pulling the tissue, they're moving around. And what we found was if the traction of the cells wasn't big enough, then nothing happened. But if you increased the traction of the cells above a critical value, you started to get spatial patterns. And the spatial patterns are where the black is where you've got a higher density of cells than where they're just spotted. Then if you change the traction even more, what you end up with is you start to get more complex spatial patterns. So we then, it depends on the geometry. And so if you have a large domain, so this is just the background before we talk about animals. If you've just got a small domain, all you can have is a small aggregation of cells. If you make it big, then you can have a whole lot of them. Then if you change the domain and make it different, make it look kind of tapered, what came out of the mathematics was that at the top end, up there, you can have more two-dimensional patterns, but as it gets near the bottom, all you can have are stripes. And so if you applied this to, say, pattern formation in animal coat patterns, what it's saying is you can have a spotted animal with a striped tail, but never, ever the other way around. And so if you end up with an animal with stripes down the back, then it tells you something about what the embryo was when the pattern was laid down. And so there's all sorts of friends and colleagues who've been looking for striped animals with spotted tails, but they've never found them yet. I'm sure they would let me know. Okay, so this really led us to think about what are called morphogenetic rules and developmental constraints. And so why do we have only 5 fingers? And this business of developmental constraints, it's fascinated people for a long time. The classical text is a treatise on teratology written by somebody called Saint-Hilaire in 1836. And he wrote several volumes on it. And people have been trying to think what forms them, how do they form, what are the reasons for them, can we explain how they arose, are they good or are they bad? And so what we decided to do was look at the vertebrate limb. And the reason we decided on that is we had some experimental colleagues, that I'll mention later, who actually did some experiments on our predictions. But the thing about the vertebrate limb, which is why I showed the salamanders, is that one really has to start thinking about evolutionary and developmental biology, which leads to the theoretical question, is how does natural selection act on developmental programs? Because that's really how we change. And that's, in other words, how do we create a limb? But what is lacking, or what was lacking, we thought, was a view of this morphological evolution that takes into account the developmental mechanism that produces the pattern. They must be connected. So, what we thought was needed, we had to go beyond the level of observation and try and come up with a mechanistic explanation of how they were all formed. And so, this is what we ended up with, is a theory of limb morphogenesis, and the central idea is associated with developmental constraints. Why are some morphologies not found? And etc. So, as I said, we talked about the basic limb. So that's what the basic limb looks like. There's the humerus, radius and ulna, and they start to bifurcate. And so if you look at the development, and some of this work was done with chick embryos, because there was, for a long time, people were manipulating chick embryos, cutting it off and seeing what happens, adding little bits on, and so on. And a major figure in this was Lewis Wolpert, a friend for many years, who didn't believe a word of this theory, and he kept doing very clever experiments to show it was wrong, but he never made it. But, we've been friends ever since. Anyway, if you think about it at the basic level, what you've got at the humerus is a single aggregation if you take a cross-section. Then it goes to the radius and ulna, and then you get the carpals there, and then you get the digits. But of course, that doesn't tell us how they're formed. And that was what we had to start looking at. And so we wanted to look at morphogenetic rules. So what we did was we took an area where the parameters and the cell traction was such that you got a single aggregation. Then we let the limb develop, and as the limb developed, what we found was it bifurcated. In other words, there was enough space and enough cells that you could actually get not just one bone, but you could get two of them. Then we did it even more, and we found, really surprisingly, that you didn't get three things coming out. What you got is one of them kind of elongated, and you got another aggregation. And we found if you do the cross-section at the end, these are the cell densities. And so what we found is we couldn't generate complicated things. And so this suggested that if you get complicated things, that's what you've got to play with. And so that's really what we looked at the sequential development in the salamander limb. And this is what we found solving the equations, and this is actually how the limb develops in the salamander. In other words, all you've got are these three rules that you can play with, and you get aggregations, etc., and you can build up really a complicated limb solely by aggregations, bifurcations, and condensations. And of course, that's how we suggested the salamander limb developed. That you get, first of all, you get a bifurcation, Then S is a segmental things. And what you do is you generate the carpels. And of course, that's still all hypothetical. So we had a friend, Per Albert, who was interested in mechanisms, and some other colleagues who said, well, have we ever thought of a Proteus? Never ever heard, I didn't know, had no idea what that was. And so what it is an example of pedomorphism, which is a slow developmental rate, which means you have fewer number of cells. And so therefore, if one looks at a Proteus, then what you get is you've got a reduction, you've got fewer digits, carpels and tarsal elements. And so when you do that, what it really we're saying is fewer cells give changes in the number of condensations, limb bifurcations, and you get a different limb altogether. Going back to Rush, that is mere speculation. So, what we did is we convinced Per Albert and Niels Schuben to do some experiments. And we took the salamander, which you saw at the beginning, and what they did was that they gave these mitotic inhibitors, which inhibit the duplication of cells. And if you look at what we predicted, this is a normal limb, the one on the left, and this is the one where they had treated it with colchicine and there were a fewer number of cells. And so what you have are fewer digits. There weren't enough to have the condensations and the bifurcations. And so if one looks at a normal limb, and then you look at fossil records, one finds that in the fossil records, salamanders actually had fewer limb buds, fewer digits. And this that you see on the top is an example of the natural variation of pedomorphism. And what we predicted was decrease the number of cells, and what you will get, and this is what we predicted, and that was what was found experimentally. So if one then starts to think, what does that really imply? I mean, what it does is one's moving evolution backwards. And so the salamanders that Albert and Schuben got are actually early evolutionary forms of the salamander limb bud, salamander limb. And so teratologies really, it was looking for developmental constraints. And one developmental constraint, the obvious one, there aren't enough cells. And so the whole business about teratologies is really, as I said, it's fascinated people for a very long time. Now, the big name in the early 19th century was Stockard, who wrote the classic paper around 1921, in where he discussed, it's a paper about nearly 200 pages long. And so what one's got, of course, are twins, co-joined twins. There's this bizarre one of the man with the thing coming out of his stomach. This is an example of scale and complexity where this hand actually has more fingers than normal. And so when one looks at the chick limb, and this is work by my friend Lewis Wolpert, and the thing about biologists that I found kind of funny, the chick has 3 digits. And I think if you weren't a biologist, you'd say let's call them 1, 2, 3. Biologists call them 2, 3, 4. It's not because they can't count, well, maybe sometimes. But anyway, it's because they think that there were five digits because that's what the salamander had. Okay, so what he did was that he did a graft so that there were more cells. And so he believed in gradients for pattern formation, so he took, this is where the chemical kind of starts, he says, to affect pattern. So he took it from one chick limb and stuck it in there. And what happened was you get a chick, the embryo chick, with 2 limbs. And so really, what one really is finding from a theoretical modeling point of view and experimental, in a sense, verification, is really that there are developmental constraints. What we found was we tried for a very long time to see if one could get something that was a single aggregation that goes into 2 or a single one that goes into 3. We could never find it. And looking at all the literature, etc., one never ever found a trifurcation. And one of the nice things about Oxford is high table. I don't mean just the food. You meet a lot of people, and I always like to find out what people were working on, etc. And at this time, somebody said, "What were you doing?" I said, "Well, I just, trying to look at these developmental constraints, and we find there's no trifurcations or 3-headed monsters." And they said, "If I can find one, will you bet a nice bottle of wine?" I confidently said, "Of course." And anyway, he then, I found this one, which is a Dicephalus. It's a skeleton 19th century one. He produced this one. But before we agreed that we'd settle on a bottle of wine, I said, "But if you do find one, this is how it would have happened. That there would be a bifurcation, and then there would be another bifurcation." And that's exactly what happened, but they called them tricephali. Okay, and so if you look in just any of the literature or anything, you do find two-headed monsters are really very common. Fish particularly so. Then there's a frog, which was, but the one I think I liked best was the chicken. And these are actually real ones. So the question is, are there any other 3-headed monsters? Well, there's a lot in the ancient classical literature. Cerberus is the dog that guards hell for Hades. And there are really, this fascinated people for centuries. And this is Pinelli, drew a dog, and these 3-headed dogs are always fierce looking. They're always just terrible because they are supposed to prevent people getting into hell and rescuing the people in hell. So they want the dogs to look really fierce. Then I came across, in the Archaeological Museum in Crete, 3 rather nice looking dogs, 3-headed dogs. But that's it. That is the only one. However, there may not be 3-headed dogs, but there are certainly lots of 7-headed ones. And this actually comes from something called the Cabinet of Natural Curiosities that was done by someone called Albertus Seba in around about 1750. It's an incredible book full of lovely pictures. Okay, let me now move on to a somewhat less cheery thing. I want to talk about brain tumours. And this is work that got started with Buster Alvor, who was the head of pathology. And he came to see me to see if I could try and model brain tumours. And he must have been about 80 at the time, and he had been in the medical world since he was 28, and he had worked on brain tumours specifically called gliomoblastomas. These are, sometimes they're called grade 4 tumours. They are the most serious brain tumour you can get, and nobody survives. And so I said to him, did he know of any case of anyone surviving from when he started? And he said, well, there is one possible case, but it's controversial. And that was over a period of 50 years. And now there is still no, and I want to show why these brain tumours are so difficult and so dangerous. And the people that got involved, I always like to get my students involved. They're all PhD students of mine who I got involved, but their topic for their thesis was always different to some of these extra, I suppose, kind of curricular things. Okay, so what do we want to do with the mathematical model? If it can be used for clinical research, then you're just trying to get grants, writing grant proposals with mathematics or something. What we wanted to do was to try and enhance imaging processes. We also wanted to show the inadequacies of current treatment. And of course, I'll come back to it. We want to know when such tumours actually start. The other aims are, we want to be able to estimate life expectancy from detection. But for other reasons I'll come back to, we want to quantify patient treatment prior to their use. The treatments are just unbelievably awful. Chemotherapy, radiation, and surgery. And I feel particularly strongly about the last one. We want to know why some patients live longer than others with the same treatment. And of course, the key thing is we want to help to design scientific trials. And I think what was encouraging, we have realized every single one of these aims. And that's what I want to describe very briefly. But just a little bit of history. The Incas, people have been doing trepanations for thousands and thousands of years. This is an Inca skull from the museum in Cusco. And what one sees, there are 4 surgeries done on this head, and they have all healed. And if one becomes much more recent, the Kisi tribe, which is probably the smallest tribe in Kenya, they do trepanations outside where the person goes and sits in a chair, and the people, they're called the Omabara, start scraping the skull until they get rid of all the bone to get into underneath the bone where the tissue is. And often it's they think to try and really get rid of some pressure in the brain, etc. It's not very medical. What is interesting is the mortality rate is 0. To a first approximation is 0. And people did this. I mean, and this is why at the beginning of the 19th century, people then went into the hospitals to have trepanations done. Then they were infected, just like now, and they died. And so people stopped doing trepanations in that way. Let me show you what a brain tumor really looks like. And how brain tumours are detected is usually something people collapse or their speech becomes faulty, whatever. They then have a computer scan, a CT scan, and they've got different words. The magnetic resonance imaging, and there are T1 ones or T2. And the T2 are more expensive, but what they do is they show up more of the tumour. And so all these scans are used, but roughly what a tumour looks like is that you have the cell density is like that. In the middle, the cells die and you get necrosis. And the red line is the more accurate computer scan, and you can see more of the tumour. And so really the question we wanted is, how do you make a model of this? And so I remember the first meeting with Buster Alvord, and I said, so, well, what causes a tumour? He said, well, there are cancer cells, there's this. And he went on, and all of these things are important. And so what I felt was, how could we make the simplest possible model? And what are the only things that are absolutely essential and necessary? And so one are the cancer cells. How do they multiply and how do they move around? And so what one did was came up with an equation which in words says you can have the rate of change of a tumor cell, and what's going to contribute to it? Well, they're going to diffuse, just like smoke particles. The cells in the tissue of the brain, the grey matter and the white matter, and the cells diffuse. And what else they do is they multiply. That's the model. And all one does mathematically is you just quantify it. And so that's just, you can think of it as a shorthand way of saying something in words. But the key thing about the model is there are diffusion coefficients. And cancer cells diffuse differently in white matter and in grey matter. And not only that, cells multiply differently. Some grow quickly and some don't. But the thing about brain tumours are unbelievably irregular. And so what one has to do is one has to take scans of the brain, of a real brain. And so although that can be a complicated model, which is actually what we used, what I thought was, if you take this tumour and you take all these scans and we get the volume of it, why don't we think that it's just a sphere? And if we then have 2 scans, we can then calculate the diffusion of the cells and how quickly they multiply. If each time we do these scans, we take the tumour and make it into a sphere, just quantitatively to begin with. We don't do that later with real patients. Anyway, you end up with an equation which is first year mathematics sort of thing. It's just a basic equation, and you can write down the solution, and the solution is just that the number of cancer cells depends on how many you started with. They grow exponentially at a given rate. This is the radius of the spherical tumor, and that's the diffusion coefficient, and that's the time. So you end up with a simple equation that people at school can actually plot. So let me give some facts now. When the radius of a tumor is about 15 millimeters, that is when it is typically detected. And so the solution of the equation says that the diameter of the tumor is going to grow, this comes from this simple form, is going to grow at 4 times the time times the square root of the multiplication times the diffusion. That's another of these things where that's just a premise. So what one has to do is one then has to say, well, how quickly will it grow? Well, you just divide r by t and you get the velocity. And so you get an expression for the velocity, unbelievably simple one that anyone can actually do. But of course, that's, once again, that's speculation. So what we did is we got data from 27, but they are low-grade tumors. And the reason that we don't have many for high-grade tumors is because people with these gliomoblastomas never ever, well, practically never let them grow unlimitedly. They always want some treatment. And so, but the one case that we do have, it is also a straight line. And that comes from CAT scan. Okay, but as I said, that's a hypothetical thing. So let's look at what a real brain looks like. These are cross sections, and this is a web page that's put out by the Montreal Neurological Institute. It's public, anybody can use it. And so this is a typical cross section of the brains that we worked with. And so this was an example of a real case. This tumor was diagnosed in 2000, and this is what it looked like with scanning, not mathematically, in July 2001. This is with autopsy. That is what the autopsy looked like. That is what came from the numerical simulation of the model equation for a real brain. In fact, this patient's brain. And that was what we started with. And this is the post-mortem scanning. And so really what one's getting out of this very simple, basic model is, this is a typical example. The problem with imaging is that you can't see it. The images aren't really sophisticated enough. And that black line is the most sophisticated imaging technique available now. And that's all it can see. And so the tumor has already gone, it's really gone all over the brain. The threshold of detection is really an enormous number of cells, and it really, one would think one would see them. Now, this, I'm not sure if this will work. This is a typical development of what a tumor looks like. No, I don't. Let me see if I can get this. Sorry, it's the Oxford thing. Anyway, let me go on to. We tried this morning and it didn't work, and we tried this afternoon. It did work. I suppose that's the way the cookie crumbles. Anyway, let me show you this. This is a movie that does work, but the other one was more for parameter values of a real. Sorry about this. And what you do is you start to see, and this is the tumor developing. Imaging cannot see it until you see the black line. And this is, and so it's up to about 125 days. You don't see anything for something like 2/3 of the growth of the tumor. Now it starts to grow. And so really, this is a more accurate picture of the thing. That is what sophisticated magnetic resonance imaging can find, and that is what the model shows based on that patient's diffusion of the cancer cells and the multiplication of the cancer cells. And so what one can do, and it really is somewhat depressingly accurate, but this is what one can do, is when a person is discovered with a tumor, and this is an actual patient, the tumor grew, and now subtotal resection is just the medical word for surgical removal. And the thing about surgeons is they want to actually operate. And so with this patient, they tried to cut out the tumor, and then, but the tumor started to grow again. Then the patient had chemotherapy and radiation, and then they can't keep it on forever. Then the tumor started to grow again. And when it got roughly up to a diameter of 30 millimeters, the patient died. And what one could estimate is if they had done nothing, how much longer would this patient have lived without surgery? So the question isn't how long will the patient live, it's what sort of life is it? And a lot of us have had, all sorts of people who have had this sort of thing, and one sees how really, what a terrible life one can have. Okay, so there was one woman, 72-year-old, who came to the hospital and she was diagnosed with a tumor. And she said, I don't want anything done. And so that, I must admit that, I mean, I learned about this. I thought maybe that was the right decision. And so she went through all the tests, the kind of tests about whether the brain was affecting things like touch your left eye with your little finger of the right hand. For up until 2 months before she died, she lived almost a normal life, except for this hanging over her. And so really it is, it really is one of these very difficult questions. Okay, let me now come to asking, when do tumors start? And you think, well, why do you care when tumors start? Well, if you think about cell phones, and nobody wants to think about cell phones, and it was a long time ago, a friend in Paris, a botanist, who actually, what he did was he took a plant that grows about this high, and just when it had got all the branches and the leaves, he took a cell phone and subjected it to 2 hours of cell phone radiation. He then followed the plant development. The branches and the leaves were totally distorted by the time it should have been normal. He's a fellow of the French Academy. He tried to get this paper published. He could never get it published because the journals that he submitted it to were frightened that the cell phone people would sue them. So, what I would recommend is that next time you buy a cell phone, read the small print. And they say, there is no evidence that this will cause any effect of brain tumors. However, and it's what you read after that, however, there is the possibility. Well, 2 years ago, a person in Washington, a Dr. Vasau, had 11-year-old children, and they took a cell phone and they put it against the children. The parents agreed. The cell phone was against their ear for 10 minutes. They then did CAT scans of the brain, and they found there was an increase of glucose practically all over the brain. Now, nobody has actually been able to say there's cancer there. But those of you who, sorry to be evangelical, but those of you who use cell phones should use an earpiece. Because I think that it must be inevitable that if there is radiation, all one needs to remember are the curies with radiation. So one of the questions I thought one should answer is, if somebody is developed with a brain tumor, when did it start? And so what one can do is you run the imaging backwards, the model backwards, and you will get an estimate of when the tumor started. Okay, just very quickly, I'll give you data on 57 patients had surgery. It's old data, but it's still relevant. 58 patients were also diagnosed, and they were not had surgery. And the effect of this was that those with surgery lived 7 weeks longer, but as I said, what sort of life did they have? So resection is the removal, and what we can do with the model is we can carry out virtual surgery. And so that's exactly what this is a typical diagnosis, but if one takes that as what is observed, we know where the tumor has gone from the model. And that's where it's gone. And so what surgeons do is that they look at the CAT scan of the tumor, and they then cut out a little bit more. Then what happens is it can be 3 months, 6 months later, the tumor, lo and behold, has regrown. Not only that, it's multifocal. And this, has been a kind of, it was one of these just mysteries. Of course it's going to be multifocal. It's all over the place already. And so it's why surgery can never work. That's what the surgeon observes. That's really where it is. And so what one can do then is you can actually work out surgery for a given patient. And this is a specific patient. You can work out when it gets to the diagnostic stage and when they die. You can get a simple formula for how long they're going to live, depending on the parameters of their tumor. Once again, we wanted to compare it with data. And the red marks are what we predicted with different patients whom theoretically we injected with a tumor that had the same parameter values of diffusion and growth as the actual people whose data was collected. Well, it's all very, very depressing about brain tumors. The problem about people with brain tumors is they go and they talk to people and they end up talking to a neurosurgeon. And neurosurgeons always want to try and cut it out. You know the difference between a neurosurgeon and God is that God doesn't think he's a neurosurgeon. And so it's really, and so what, and I was giving a lecture to a bunch of doctors once, and afterwards one of them said, I said to him, well, I mean, you do brain surgeon, and I said, why on earth do you do it when you know the patient's not going to survive and it can be a miserable life afterwards? He said, if I don't do it, somebody else will. That's what it's about, I think. Not always, no, I mustn't be. But anyway, to conclude this thing, it shows these brain tumors aren't unpredictable. They really, in the model, it suggests new way to study them. It still doesn't say what we can do about them, but unless we know how they spread, we're not going to know how to actually cure them. We can now estimate really when the tumor started. Not only that, we can actually quantify how it grows and spreads. It's an explanation of why some patients live longer than others. The values of the diffusion and the cancer cell multiplications are different. Not only that, we find young children live longer because it turns out that the parameters associated with the growth of their tumours are such that the tumour is more contained. And so it means that they can actually live longer with radiation, which kills more of the cells, but the end result is unfortunately the same. We can quantify the effects and the side effects before the patient has any treatment. And that really is, I think, is something that helps. Anyway, we're now currently gathering a large number of patients with different grade tumours, and there's a kind of small clinical study going on. So let me finish with Henri de Mondeville again. And I think he was an amazingly practical man. He was the surgeon to two kings, etc. And as you saw, he had a low opinion of people, but he did like surgery. And he said it's surer, more preferable, more noble, more perfect, more necessary, and more lucrative. That was in the 14th century. And okay, let me talk about something a little different, just to fit. I'll do this quickly. The collaborator was main collaborator with John Gottman, a clinical psychologist, who wrote to me when I was in Oxford, still in Oxford, and said he wondered if I could maybe try and make a mathematical model about marital interaction. And I thought it was a pile of rubbish. And ended up in Washington, we had lunch together, and I got kind of hooked. And the thing about divorces is there are millions a year, and there is now a huge, enormous legal industry with lawyers who specialize in divorce of couples who come from different countries. So for example, if you live in Texas, it's better to be a man. If you live in France and the man has been having an affair, then it's kind of half and half. There are some countries where the man can get a divorce and the wife doesn't even know it until she gets the papers. It is unbelievably complicated. And so once again, I got a bunch of my students, Jane White, Jane's now in Bath, Rebecca Tyson, who's in Canada, and John Gottman, after the results of all this, retired early and started up a clinic for marital therapy. Okay, so what do we do? Well, first of all, the people that we got for this study were people who applied for a marriage certificate in King County in the state of Washington near Seattle. They were invited to partake in a study associated with marital interaction and divorce prediction. And all they had to do was come to the department and sit opposite each other and be filmed talking about a problem of contention. Absolutely made no difference what it was. I mean, food, sex, in-laws, you name it, it made absolutely no difference. Okay, and so what we did then was we scored what each of them said. And there is a scoring system, and you assign an integer between +4 and -4. And this, what you then did is you counted the positive things and took away the negative things each time one of them spoke. And this was, the data was gathered mainly by psychology students who sat behind a one-way mirror, and the couple knew they were being filmed. And usually within about a minute, they'd forgotten everything except what they were arguing about. And so these 6 students, it was amazing how close they were in getting the same numbers. And so what you get each time they speak is you get a number. So you end up drawing a curve of a kind of Dow Jones average. I gave a talk about this, and then somebody in Australia sent me a cartoon, and that they wanted to show whether this test will show whether or not they're going to get divorced. And they had to choose a topic. That was what they did. Okay, this is what the scoring system is. And it is amazingly easy to assess the numbers. They're also associated with visual things about whether it's anger, contempt, humor, etc. And this is the 16-code system. And so what one gets is you get a kind of Dow Jones average of the conversation. So in this case, that's 0, and it becomes progressively more positive. And so it's roughly a 5-to-1 ratio of positive to negative. It's a very stable marriage. That one, on the other hand, and so that is a ratio of about 0.8 positive to 1 negative. And this couple actually did end up getting divorced. This is the data. Between 1992 or 2004, we actually studied 700 couples. And we analyzed the thing, and what we found is the number of the different marriage types were very limited. There were only 5 of them. And what we predicted was whether they would get divorced, stay married, either happily or unhappily. Then every 1 to 2 years, we sent out a questionnaire, and they were asked to complete it. We then compared the predictions with what the facts were. So this isn't statistics in the sense that you do a small study and you then expand it. These are real numbers that we got. Well, the prediction of which couples would get divorced was actually 94% accurate. It was even better than that in the sense that those we predicted would definitely get divorced, we were 100% correct. It was some who predicted we'd stay married unhappily, ended up getting divorced. And most of them actually got divorced within 4 years. Of course, we couldn't possibly tell them anything about the predictions. Okay, this is, for the therapy, we had to develop something that would show people who did not have any kind of background, they just knew they were having a terrible time. And so they're shown a picture about the numbers that they would be shown later. And so we got a couple of actors to show it. And this stayed in this quadrant, they're both happy. And in that one, they're both very miserable. Right? That one, the wife is happy. And so what you get from the data is something that you can actually show has a specific meaning for how they are interacting. And so just to, again, I don't know if this movie will work. Let me see. This is typical data from one couple. And the numbers look as if they're going all over the place. And after one had seen about 25 of these couples, we could look at this data and say, we're going to get divorced. But of course, that's no good. One has to actually be able to quantify it. So let me briefly describe the model. It's an intuitive model, and this says that the husband can influence the wife, and this is the score that I described. After the husband speaks, that's how she felt before, and that's something I'll mention just later, is how they interpret their view of the marriage. And so you can put this into a simple mathematical model, and that's what you get. And what we want to do is evaluate all these parameters, A and R. And this means if R is about 1, it means the wife isn't very interested in changing her mind. If R is near 0, then it means that she can be influenced by what the husband says. And so you have that equation. And this influence function is how we actually describe marriages. And so that is typical data that the husband, when the husband says something, this is the influence that we were able to evaluate from the data obtained from the 15-minute conversation. So you can put a curve, a kind of best fit curve, but that's very complicated. And so we decided, let's not bother with that. Let's just take near the origin 2 straight lines. Of course, what is really curious, that totally surprised us, is here the husband is being incredibly positive. The influence on his wife is negative. In other words, she's starting to think, what's he trying on? And so, but the fact that this happened with the vast majority of these 700 couples, it just was a somewhat surprising phenomenon. And these are how we quantified the marriage. And these are just 2 examples of the wife's influence on the husband and the husband's influence on the wife. And so this is a typical thing that if the husband says something, if the husband says something positive, it has a positive effect. If he says something, it has a negative effect, but less negative. That is very common in marriages. And so these are 2 examples of the influence numbers for what are conflict-avoiding couples. That when they say something negative, the influence is much less than if they say something positive. And these are numbers, as I said, that actually come from the data. And so that's a theoretical conflict-avoiding couple. They have little effect on each other on the negative side. So, then there's, when we looked at these 700 couples, there really were only 5 types of marriage. 3 stable ones and 2 unstable ones. And the characteristics are the volatile ones, some of them were stable, but generally they were unstable. You know, they have heated arguments, romantic, etc. But then the ones that really were stable were those that were calmer, intimate, shared experience rather than individuality, and they were the ones that really stayed married. The avoiders were also stable. They didn't want to argue when one of them was being negative. They tried to pacify them. The hostile ones are when you get mixed marriages. And hostile detached is the husband gets wildly excited and the wife just kind of keeps calm and says, well, maybe you're right, and so on. These marriages really don't last. So basically what one's got is we have these things, we have the data, and we evaluated the parameters. In the marriages, part of the time they didn't influence each other at all. Then you end up with a model equation and you say, what is the steady state? And so you can just say, so in other words, they don't vary, everything's the same, you solve it, you get that, you solve it, and the uninfluenced steady state is just a parameter A over 1 minus R1. R1 has to be less than 1 for mathematicians because it's a discrete equation. These are the parameters that we evaluated. You get the same for the husband. If A is less than 0 and B is less than 0, they're almost certainly going to get divorced. It was that simple. So one uninfluenced steady state has to be positive. And this inertia things are, as I said, if R is near 1, it means they're pretty rigid in what they believe. Now, what one can do is, I don't want to do any of the math, but from these equations, you can get what are called Nulk lines. And these are just lines that if you vary H and W along these lines, you have a constant. It's kind of constant. So you have one of these lines for the wife, you have one for the husband. Where they interact are the steady states of the marriage. So in this case, the black line is a stable steady state, and that is in the first quadrant. There's another steady state which is unstable, and so if they ever end up in this third quadrant really getting irritated with each other, very quickly they end up leaving there, it's unstable, and they move up to a stable steady state. So what one can do with this is, this is crucially dependent on the uninfluenced steady state of the wife and of the husband. So suppose the husband gets a little more less happy with the whole situation, then what happened? I mean, in the happy state, here you've got this, it's a thing in the bodily, you know, that's a happy marriage. I don't know what they're doing in the bushes, but anyway. But if the husband becomes less satisfied with the marriage, then he moves, his steady state moves over into the negative region. And that influences the steady state. And so instead of really being very positive, the husband's not very happy with it, but the wife still putting up with it. If the husband becomes even more unhappy with that, what you end up with is there's no steady state. And so it depends how I mean, it can either be, you know, the result can be some, you know, I don't know, sort of, you know, delightful mutual, you know, sort of orgy, or some kind of Calvinist hell. But basically, what one gets in this very simple model is you can actually quantify certain things about a marriage. Of course, I don't know who was it that said about never go to bed angry, stay up and fight. I don't know who said it. I think it was some American comedian, but I think it's probably Groucho Marx's comment. He said, you know, it's inevitable. Marriage always interrupts and influences and affects romance. Because if you have a romance, your wife is certainly going to interfere. And so so there's all sorts of quite nice quotes about these things. Okay, so just the last few slides is I did it with straight lines, but the real numbers of these lines are really they come from the data, they're complicated, and that is a typical stable marriage. And if they start anywhere the conversation negatively, it always ends up at the positive steady state. Very stable marriage. In this case, the stable states are negative, and it doesn't matter where they start, they always end up there. Well, the data that I showed you, that couple, their steady state was in the third quadrant, and they actually got divorced. So what can one do about therapy, just to finish? This is where the couple, the steady state of their interaction was negative. And the thing about this is that they are both negative, the probability is high for divorce. And in fact, that's exactly what happened to them. On the other hand, this couple, the wife was a bit positive about it, the husband wasn't, and so they actually, that really is a couple where it is a candidate for therapy. And they actually had therapy, and this is what their score was beforehand, the data. So in other words, they started talking, and the wife became more negative, the husband was negative all the time. And They then had therapy, lasted for, I can't remember exact, 2 months or something. And they then did the test again, and the steady state was in the first quadrant. We then actually gather the data of them, and this is the data. I mean, it might not be joke a minute, but at least the, one of them's positive. But I think what was interesting, it's if one of them is positive, then it can be a candidate. So what have we actually gained from all this? Well, therapy is one thing. That they are shown the data, they're shown the videotape, they're shown the predictions, and anything they couldn't understand was explained specifically to them by the clinical psychologist. And this therapy is based almost entirely on this very simple model. And so, really, as I said, these are the results. It's a new language for discussing psychology. And what I should add here is, I remember a long time, it's a friend, Christopher Zeman, who most of you will know. I remember talking to him, he talked to me about really the social sciences. And I thought at the time it was a load of rubbish. And he was absolutely right. I mean, he applied it to different things. But anyway, so we can use it for that. It's a rationale. We found there were only 5 types of marriages. Stable ones have got matched interaction style, and unstable ones have the other kind. But basically, the last thing slide I want to really show is, I quoted Benjamin Rush. In fact, Montaigne had a much bigger influence in a lot of what I have done in this field, where, as he says, I'm not afraid to confess it, he would offer a candle to St. Michael and, if needed, another to his dragon. And I think, in a sense, that's what applied mathematics is. The reason I wanted to show this thing, this is a portrait in the Bodleian. A different view really came from, I thought the only pure mathematician I could quote was maybe somebody in the 19th century. And as you can read it, we find the primitive source of rationality. Mathematicians must turn to biologists. How can they otherwise carry out their experiments if they don't know any mathematics? Well, when one does interdisciplinary work, it's rather difficult to have that attitude. And I thought this picture really kind of summed up what a lot of people who have worked in this field is a certain kind of arrogance. And I showed this to a friend, an Australian friend, who then sent me that picture. But basically, what it is, I really think if one keeps the mathematics as simple as possible so that you can explain it to people who are not scientists, then maybe one's got a chance of actually doing something. I suppose the trouble with mathematicians is sort of 99% of them give the rest a bad name. And so maybe so I think that is probably the appropriate place to stop. Thank you very much.